Thank you very much. It's always a pleasure to give a talk to the audience who is also passionate about quantum. And I want to tell you a story why I'm passionate about quantum and what in particular is interesting for me in quantum technologies. I'll touch several points. So first I'll take, let's say, why quantum and what it can bring. So a few words about short algorithm, and then I'll touch a topic of post-quantum cryptography, and then deep dive in quantum communications and what I do personally and in particular. So going back into the history, so we should remember Richard Feynman, who proposed the idea of quantum computation back in 1982, and 12 years later, Peter Shor proposed first quantum algorithm, which attracted a lot of attention from the community, because this algorithm was focused on breaking cryptographic codes, and that's a story of quantum communication. And yeah, Richard Feynman himself worked mainly in high energy physics and in particles. Personally, I started my career in the university from particles, even participated in the collider experiment, but then shifted to quantum communications. And one of the main reasons was that it's becoming more and more practical. Meanwhile, the high energy physics is very beautiful on the theory part, but it's not going to be practical in let's say, few decades. And if we talk about quantum communications, what is very interesting that things happened for quantum communications, even in advance to quantum computation. So the first idea of quantum communication was the quantum money, which was proposed in let's say 69, 70, and published at 83, and later in 1984, the year when I was born, was proposed the BB84 protocol, which answered the question which was raised 10 years later by Shor's algorithm. So it's very interesting that at the moment when Peter Shor invented algorithm, in principle, we already knew what to do with it. So yes, and if we step like 40 years forward, we will see that now quantum computation is a billion-dollar industry. Companies are raising like hundreds of millions of investment. And that's a big reason behind it, because it is promising to revolutionize many areas of human life, like medicine or new materials building. At the same time, full scalable quantum computer, when it will be built, it promises to break today's cryptography. By the way, like many other high-end technologies which are still not reached its goal, on the way of creating quantum computer, people are creating many other useful things like quantum-inspired algorithms, which in principle today demonstrates solution of some problems like financial portfolio optimization faster than existing algorithm. people started to do optical matrix multiplication while like create on the way of creation of quantum computer. And also very interesting topic is reservoir computing, which is promising, but yeah, that's still a big deep dive to be done. So going back to communications, before talking about why quantum communications are so important, just I'll make a quick reminder from classical cryptography. So when you pay with your credit card, doing it like few times a day or accessing any website, the asymmetric key agreement happens. So the pair of public and private key is generated, and using private key you can encrypt data. Using public key you can encrypt data. Using private key you can decrypt data. And it works for decades, but the problem of this scheme is that classical information can be copied, whatever it is a piece of paper, digital information, or some light signal into the fiber, allows you to make an exact copy of your digital information and store it for a pretty long time. And all this information can be stored long enough to realize the Shor algorithm, decrypt the private key, calculate the private key using public key, and then access actual data which was stored. And that's so cryptography people say that it's not a hypothesis, but there are already existing data centers which are doing this job of storing encoded information for the future decryption. And then how can quantum help in this case? And the main difference between quantum and classical for the quantum communications is that you cannot make an exact copy of quantum state. So that means if you try to make a copy, first of all, copy will not be ideal. And the second point, if you use, of course, non-orthogonal states, you will damage the initial state you made a copy. And if somebody like mentions you that it's like beyond imaginable technology, that's not true. In principle, you can put an atom into the cavity, couple it strongly to the light field, and put the light into the cavity, make a light interact with atom, and change its state. Of course, as soon as light interacts with atom affects the light, and as a result, you have two states, but changed. So it ends up with very straightforward non-cloning theorem, which is very easy to prove. So you have a machine which should make an ideal copy. You have 0 and 1 state, the blank of the copy, like piece of paper where your copy machine makes a copy, and state of the copy machine. And suppose that after the process you have an exact copies, but then you try to make a copy of superposition state. So remember, once again, non-orthogonal states. And it appears that if you have 0 plus 1 state, it does not end up of once again 0 plus 1, because 0 plus 1 and 0 plus 1 is the product is not equal to 0, 0 plus 1, 1. So you lose your cross correlation states. And what can we do? We can go back to our cryptography key concept and use a single photons to carry individual random bits and send it. So if somebody will try to measure it, to make this non-ideal copy, we will see we can actually detect this attack. And if it happens and we detect it, we just discard this key. What is very important at this stage, we are not sending useful information. We are sending random bits, which would be a symmetric key. And if it passes all tests, and we can, let's see, as I like to say, guarantee on the level of quantum mechanics that it's known only to the transmitter and receiver, conditioned that you realized in your hardware, that you exactly realized in the hardware your theoretical quantum key distribution algorithm. And the first and the most well-known is BB84, which was proposed 40 years ago. That's a very popular picture. And what is important on this picture is that we once again use non-orthogonal states. So we encode the zeros and ones in orthogonal states, let's say horizontal and vertical polarization. But we also use a rotated basis, which represents 0 plus 1, which was mentioned in a non-cloning theorem. So we use diagonal and antagon-diagonal polarization. Then we send these random bits and encode it in random bases, and they are measured in random bases. And sometimes they are measured successfully, sometimes not. And then after the photon measured and it does not exist, we announce the basis and can retrieve the correlated data. So if somebody will try to make an intercept resent attack, he will introduce 25% error. Why? Because in 50% of cases, the guess of the basis would be correct and there will be no error. In 50%, the guess would be wrong and the output would be random. So 1/2 of 1/2 is 25%. That would be an error rate of like just very brutal attack. But what about quantum capabilities of an eavesdropper? So if we suppose to use something to protect from quantum attack, we should be very paranoid. That means that we should give to the eavesdropper all future available technologies. And that means that we can just write draw some universal quantum machine, and in principle, eavesdropper has it. Honestly, today's technology are not so far from this like universal quantum machines. There are experiments by Nicolas Jezan who used very low noise optical amplifier to do such a copy. And he found out that, of course, he cannot reach the quantum limit accessible by universal quantum machine, but he can go pretty close to this level. So introducing some universal quantum machine, the good thing is that quantum theory, quantum information theory allows us to set an upper bound of eavesdrop information dependent on error rate. So that means that we can measure actual bit error rate, whatever the source of it. So even we understand our equipment is not ideal, our the formula is a little bit outdated because it's for individual attacks, but we can prove it also for collective attacks. And the actual key is the difference between the mutual information between transmitter and receiver and intercepted And if droppers information, it gets here about around 15%, but it's more known, let's say 11% limit, which refers to infinite key with collective attacks. But then, of course, we try to take into account all non-ideal cases like finite key size, and I would don't deep dive in it, but today theory allows to take into account even non-ideal properties of the hardware. And yeah, it was initially the proof of BB84 was based on the Eckert protocol. So first of all, there was a proof of quantum key distribution based on entangled states, and then we suppose that we prepare and measure one particle totally in transmitter, and then prove equivalence between such a system and preparation of one. So if you try to tell this story to people from industry, they would say, okay, it's all very beautiful, but there are no quantum computers capable to break today's asymmetric cryptography. So please come later when asymmetric cryptography would be broken. And the answer on this question is very simple. It's called Moscow inequality, and it takes into account that there is a forecast of times that quantum computer may break classic cryptography, and of course that's a probabilistic model. I can say that it can happen on 5-year horizon, but with low probability, or it can happen on 20 years horizon with pretty high probability. But at the same time, there is a migration time of existing information security infrastructure, and that's the time of your data to be secure. So if these two numbers are large, then it's time to action. And if we look at the dynamics of quantum communications now, it is time to action, because the migration time, it's not just a simple update. It's like piloting projects. It's analysis of network architectures. It's hardware installation, integration, and of course things like policy updates. So large systems cannot be changed quickly. And of course, the time which data needed to be secure depends on the type of the data, and things like medical information should be secure for years because it's like sensitive personal data. So now the decryptlator attack is not something virtual. It's something which people need to care about, and agencies like NIST and CISA in United States already announced the sense of urgency. So they encourage all companies to make a due diligence of their make it actually today the due diligence of their infrastructure, understand where there is a quantum threat. But NIST proposes as a solution, first of all, the post-quantum. Okay, so what else can be why should we expect that quantum communications will be important soon? As the dynamics of quantum computing. So companies like IBM and PsiQuantum show the forecast which many people can consider over-optimistic. At the same time, like just lucky technological breakthrough can change the game in a few months. And what is interesting, like in recent publication, people started to talk about logical qubits. So there are, of course, people may argue that it's more like scientific marketing when Mikhail Lukin publishes his paper and says that he has already done logical qubits, because the logical qubit is something, it's either some qubit with error correction or a qubit which can live infinitely long. So there is still area for discussion. But at least people started to use in scientific publications the term logical qubit. The next reason is that if somebody breaks cryptography, he is not obliged to tell you about it. And there is a well-known story of Enigma when it was actually broken in 1938 or 39, something like this. But it was publicly announced that it was broken only in 70s. So more than 30 years, it was top secret information. The fact that it was actually broken. And if somebody makes a scalable quantum computer and keep it secret, we can mention it by appearing a lot of new materials or other evidences of a great success. But at the same time, that's the case. And the reason number 3, which is still valid, if you use asymmetric cryptography, there is still probability that somebody will find an optimal algorithm to break it without any quantum computer. So yes, Peter Shor has found a first quantum algorithm, first algorithm to make an optimal factorization, and it requires quantum computer, but there is no mathematical warranty that nobody will find such an algorithm for laptop. And interesting trend is related to another big area, which is called AI. And for example, for a long time, people believed that there is an optimal algorithm for matrix multiplication. But recently, Google used DeepMind to approach this problem solving and found many new algorithms which were more efficient for some particular matrices to multiply. Oh, sorry, I missed the slide. Yeah, that's this slide which I was talking about. And yes, the other reason is that the quantum algorithm itself, both quantum and classical algorithms, are trying to optimize this problem solver. So also, not obligatory Shor algorithm would be the one which solves factorization problem for large number first. Maybe there will be other more optimal algorithms. So when you try to do something practical, so there is a big motivation to start doing quantum cryptography now, but people in business say, first try to look what alternatives are available. And first of all, there is a very straightforward alternative, which is called a trusted courier. So you can always send a keys with a person. Already, I remember that's like about a decade ago, bank gave me a list of one-time passwords you need to. It was protected by by thin foil. You remove it by a coin and used once to authenticate your transactions with the bank. So that's still possible. But the problem is that if you need to pay something now, but you run out of this one-time password, so you, let's say, in another country, it's pretty hard to get quickly to a bank and go back, especially if like things are getting faster and faster in today's economy. So another approach is post-quantum cryptography. And this approach looks for classical algorithms, classical problems, which easy to calculate one way and hard to calculate another way. So there is still mathematical complexity. But the good thing is that it can be implemented in on a software level, and it can be done pretty fast. But when I talk fast, I mean it can be done fast on some particular problem, like on some particular application. But today there has been started migration from RSA to post-quantum, and large companies are investing huge money on technological analysis of all their millions of lines of code to search for cryptographic primitives and to identify it as and build a schedule of replacing it from quantum to post-quantum. So many people argue that we don't need quantum cryptography at all. The post-quantum is enough. And there is a well-known letter by national NSA in the United States. It has been like for a few years. And recently, the German BSI, also French and Swedish agencies announced the letter when they identify problems of quantum cryptography and says that we need only post-quantum, we don't need quantum. But we opened these documents, looked at the problems which were identified, and that's actually a to-do list for today's researcher. That's to-do list for theoreticians who search for new algorithms. That's to-do list for experimental people. So that's they identify that the high-cost the quantum key distribution is a high-cost solution. It's distance limited because your photons actually lost in a media, in a fiber. You need a trusted nodes to build a scalable network, and trusted nodes needs a protection. You need an authentication, and it's hard to certify. So the hardest point is a trusted node. Because if you look at today's quantum networks in China, in Europe, and in many other places, they're built on trusted node approach. But also, like that's a motivation to build quantum memory. And if we put all together this to-do list, so we can increase distance, we can use an entangled state QKD. In entangled states, at least one node can be not trusted. You can use MDI or twin field approach, which can increase the distance or make some one node untrusted. We need to invest in quantum memory, which will allow us to build quantum repeaters. We need to build satellite quantum key distribution, which will allow us to connect any user on the ground. And even transportable quantum memory startups has already appeared. So what people are saying about is literally generate pairs of states, store it in a box, put it in the truck or in a plane, and move to another place. And it's not they consider it not a futuristic picture. They consider it to be today's technological challenge. I know at least one startup in the United States who is focused on this task, and also one speaker from China has announced it like one of their priorities. So let's go further. So if we talk about post-quantum cryptography and its certification, there is still big challenge. There is still like very bright events, like CYC protocol was broken, and it was one of the leaders of NIST competition for post-quantum. The crystal Kyber application was broken, so luckily not the protocol itself, but implementation was broken. So that means that the post-quantum cryptography also has this certification problem, and also has the threats of purine and new algorithm to break it. Of course, when we talk about quantum key distribution, there are engineering implementation problems, and there was a well-known experiment which was done here in Singapore when Vadim Makarov has built this box and has broken the actual implementation, engineering implementation of quantum key distribution. And what does it mean? It means that it doesn't mean that quantum or post-quantum cryptography is not working. That means that there should be proper analysis of actual hardware, and we should work on solutions which intrinsically would be easy to certify. And what is good thing that in last year, ISO has announced the actual standard for quantum key distribution, even before the NIST ended up its process of announcing the post-quantum algorithm. So we could say that on the certification side, quantum is even faster than post-quantum. But that doesn't mean that we should say quantum or post-quantum. We should say quantum and post-quantum should work together. Post-quantum as lightweight software solution should be everywhere, and on the most important part, it should be quantum key distribution. So these technologies should not be considered either or. It should be used together, because its vulnerabilities are in different dimensions, because the attack on quantum key distribution is actual physical attacks on a fiber, and attacks on post-quantum is something which can be done software and remotely. Before jumping in, let's look what can we see on the market. Why should we do as a scientists quantum communications if we can go and buy actual QKD devices from Toshiba, Quantique, or Quantum Cetek? But these devices, they work to 100 to 120 kilometers. They generate enough key, but they cost pretty much. That was what mentioned by the agencies. So we decided to do our own solution. So what we did, we made an entangled state QKD. Now we reach this, what we call ready for implementation. We integrated with classical encryptors. We demonstrated the key distribution over deployed fiber, and we put it on the rack. I hope that in UAE very soon we'll have the actual demonstration of quantum key distribution. And if you look inside this entangled state box, you will see this polarization entangled state generation, the same approach which is used here in Singapore. We pushed a little bit forward the brightness of the system. We have about 60% of heralded efficiency, and on the short distance, about 2 meters of fiber. With APDs, we keep 50,000 clicks a second. We don't push and that we still limit our laser in brightness not to saturate single photon detectors. And if you go look inside the receiver, there are we tried to build with all off-the-shelf components except the polarization projection system, which is made by ourselves. But inside the box, there is single board computers, there is time to digital converter, and 4 ID quantique single photon detectors. And it works pretty well, but it's still costly compared to the post-quantum and costly compared to classical encryptors. So yeah, here it's our we have done an integration in classical communication system. We have a good dashboard, and we integrated in a Fortinet encryptors. So it's still much more expensive than classical encryptors, which provide you 10 gigabit classical communication. But the good thing about the entangled state QKD is that you can give an entangled state source to the telecom company, and it will literally sell photons to the clients in the city. So what's next? If you look also into the state of the art, we will find that there is high quantum key generation, quantum key rate was demonstrated up to 100 megabits per second. So for previous record was done by Toshiba, it was 10 megabits per second. Now it's Chinese record, it's 110 megabits per second. There's 1,000 kilometers for twin field QKD in China. And of course, there is a satellite QKD. Also, right now, only Chinese satellite is available, but we believe that in the end of this year, beginning of the next year, there will be more quantum satellites. So based on what we found out, we decided also to do our own ground station. And the good thing about what we want to do about our ground station, we want to make it compatible between different satellites. Because if, for example, we want to connect UAE with, let's say, Australia, but no UAE, no Australia has their own quantum satellite. What they can do, they can trust somebody who has quantum satellite, but then they trust the company which is placed in third country, or they can use 2 different quantum satellites from different providers from different countries, and the probability that they will take the key and speak to each other strongly decreases. So now we have the dome. We installed the telescope, and we are training to track properly the satellites. Next step would be the installation of the actual single photon detecting system and track the reflected light, and then we'll go further to this system is also capable for the classical communication satellite to ground. We support at least 3 standards of classical communication and at least 2 wavelengths of quantum communication. What else? I mentioned several times the problem is that the quantum key distribution is very expensive. And it's expensive in In comparison with what? It's expensive in comparison with classical cryptography equipment, which people actually use. So if we go to Amazon and try to buy 10 gigabit encryptor, it will be about $8,000 to $10,000 per box. So pair to connect to two sites, you will pay, let's say, $16,000 to $20,000. Meanwhile, if we talk about today's point-to-point QKD solutions, that's hundreds of thousands. So one of the solutions is to make put one receiver, introduce optical switch, and connect it to many transmitters. At least we share the price of the receiver, which contains complicated single photon detectors, between many lines. And that already allows to decrease the cost. We looked at the market and found out that there's some empty niche, that people are actively building quantum networks using this expensive solution, but there is still nothing to put the last mile to connect the node of quantum network and to connect user in the city. So we decided to focus our research on the solution which will not compete with others on distance or key rate, but will compete on the simplicity of the transmitter device. And we ended up on using the so-called passive state preparation. What it is, if we look about existing quantum key distribution solution, what people do first, as I said at the BB84 protocol, we need to send random bits. And the best random bits are done using quantum random number generators. But to do it at a high repetition rate, first you need to prepare random quantum state at a very high rate, then measure it, then amplify the output, digitize it by analog to digital converter, post-process on high-speed system, and then use these numbers once again with digital to analog converter, amplifier, and electro-optical modulator to modulate actual light. So that's a very long chain. And that's why the traditional approach to make QKD transmitter doesn't allow to make it affordable. But let's say we started our story from preparation of random states. Why not to use these random states as actual qubits? So we can prepare random states, take a small fraction, send it to the receiver, and make a local tomography to measure it. And this system would be not only easier to make, but it will also have additional protection against the so-called Trojan horse attack, because you don't have active modulation. That means that's nothing to probe in this system. Of course, there is a so-called laser seeding attack, but it's common for both for all systems except entangled QKD systems. So we made this tabletop experiment. Now we used our deployed fiber up to 10 kilometers, and we prepare a time-bin qubit. So there are many quantum random number generators which use a gain switch laser and then measure the random phase between laser pulses. And it's like there are a lot of publications proving that the nature of this random phase is quantum. But here, once again, in QKD, a lot of people are using time-bin qubits with random phase, but phase takes 4 different states: 0 pi, pi over 2, 3 pi over 2. Here we prepare the random state on the whole equator of Bloch sphere, split small fraction, and send it to the receiver. And on the transmitter side, we can make a classical measurement. So as soon as that's a strong classical light, we can measure the phase difference. The only problem is that you want to distinguish not 2 states, but 4 states. If you make an imbalanced Mach-Zehnder interferometer, it will allow you to distinguish only 1 basis, 0 and pi. And in other bases, it will the states will give you a similar output on both detectors. So what can you do? We decided to convert the state from the time being to polarization. So we made a delay line, and as I mentioned, we tried to make a transmitter as simple as possible. And simplest interferometer is not imbalanced Mach-Zehnder. Simplest interferometer is a loop. And this loop allows us to meet in one time domain the early and late state, but there are in different polarizations inside the fiber. So then we take it out from the fiber to the free space and actually measure this output. So obtaining the polarization states, we can distinguish between 0 and pi, which will end up with diagonal and anti-diagonal polarization, and pi over 2, 3 pi over 2, which will result in circular counter-circular polarization, which we can distinguish with assistance of the quarter wave plane. So we received not very high bit rate, but at the very beginning, we focused to use these 10 gigabit encryptors. And we asked the manufacturer, how much key do you need? The answer was 1 256-bit key per 2 minutes. So you don't need 300 kilobits per second provided by Toshiba. You need few bits per second. So that means that we can use an optical switch and generate, if we have on average, let's say 500 bits per second, we can connect 100 users. Each will have 5 bits per second on average, and that will be enough to connect everyone using standard 10G encryptor. So now we have not very high state preparation rate. Next generation will be about 50 megahertz state preparation rate, and they will achieve the required bit rate. That's tabletop experiment, but it uses the deployed 10 kilometer fiber. And we can optimize the system. Of course, if as a post selection decreases number of states we prepared. Let's say we prepared with 1 million of states per second. If we take only 10% of it, then we end up with 100,000 of prepared states per second. But we can tune it by using the threshold of comparator in the tomography system on the post selection. So more strict our state preparation, less the quantum beta rate, but of course less states we prepare, and we can optimize this for particular line. So yeah, thank you very much.